Hello, good people. Welcome to the first video of topic 5.3. Before we get started, I just want to clarify some things. Not really clarify, just make it more explicit. The fact that when we finished Unit 4 was about applying all of the derivative rules that we had learned how to do. We had learned how to take derivatives in Unit 2 and in Unit 3. And Unit 4 says, okay, so now what are we going to do with them, right? So it gives us some context for taking those derivatives. So Unit 4 was about applying derivatives in a contextual situation. It was always about something going on, whether it was related rates, whether it was the motion problems, whether it was find the instantaneous rate of change of a function, and that function is measuring the amount of people coming into the library or whatever that is. There was some context involved. In Unit 5, we're going to continue, and this is kind of like the last big unit of derivatives until we get to differential equations, but we'll get to that in spring. The idea here is that we're continuing to take derivatives. So we're going to use the rules that we learned how to do in units 2 and 3. But now we're doing it as we investigate or analyze functions. So we're going to be looking at how functions behave, whether they are increasing or decreasing, whether they achieve maximum points or minimum points, whether they how do we optimize situations and find those maximums and minimum points. The very first unit, or the very first topic for this unit, was the mean value theorem. And the mean value theorem told us that there exists, if my function is continuous on the closed interval and differentiable on the open interval, then there exists a point where the derivative, the slope of the tangent line at that point, is equal to the average rate of change, the slope of the secant line. So right there, we started to put together some ideas about a function that were given either in terms of an equation or in terms of a graph. So the purpose of 5.3 and in conjunction 5.4 is to analyze when do we know if a function is increasing or decreasing, and knowing that, can we make some conclusions about the special points on the graph? And so we're going to look at this graph here, and we're going to ask the question. Here's a graph of f of x. On what intervals is the function increasing? And on what intervals is the function decreasing? So one thing I want to make clear from the very beginning, when it asks for intervals, it's asking for x values. When it asks for intervals, it's asking for a window of x values. And so I'm asking, on what x values is the function increasing? Well, by looking at the graph, I kind of see that the graph is increasing here. I'm going to put INC period for increasing. And I'm going to say that the function is increasing here. And as I finish tracing this, and by the way, this goes on forever, right? This is INC. I'm going to go ahead and write down the x intervals where that happens. So my function is increasing on x's that are between x equals 2 and x equals 5. That would be this first section, that line segment. But it's also increasing for x's that are between, well, the function keeps going up forever as we move to the right. So even if I were to go up to 12, my function would be increasing. Or if I went out to 20, my function would be increasing. If I went out to 100, my function would be increasing because I see this arrow telling me that it continues in that behavior. So we're going to say for x's that are greater than or equal to 7. Now, visually we can see that the graph is increasing, but what is it that tells us that a graph is increasing? For that, think of it this way. If I pick any 2 points in either of these blue sections, if I pick this point and this point, would you agree that the point on the right, that would be this, or the second point, is higher than the point on the left, or the one on the left? Would you agree with that? Because that is the definition of increasing. A function is increasing if f of x2 is greater than f of x1 when x2 is greater than x1. In other words, the y value of the second point is bigger than the y value of the first point when the second point is a bigger value than the first point. This is just telling me that x2 is on the right side of x1, right? This is telling me that the y value is higher than the y value of the first point. Now, I said x1 and x2. I just chose those two random points, but it can work for any 2 points on this blue section, right? I can choose a point down here, and I can choose a point up here. This would be x1, and this would be x2. I know that because x2 has to be greater than x1. So x2, which is a little bit more than 4, is definitely bigger than x1, which I'm claiming is 2. And the y value, or f of x2, is higher than this y value, which is f of x1. Mathematically, this is the definition of increasing. Okie dokie. If that's the case, then where's the function decreasing? Well, the function is going to be decreasing in this section. I'm going to say DEC period for decreasing. And it's also decreasing in this section. And I'm going to call that DEC, decreasing. So you can see that the function is increasing, where the function is increasing, where it's decreasing. And intuitively, or maybe because of the work that we've done in previous math classes, we can kind of see that, yeah, that makes sense. Okay, so then what are those intervals? Well, for decreasing, that would be x's that are between -3 and +2, or x's that are between +5 and +7. So my blue parts are where it's increasing. These are my intervals of x where the function is increasing. My red parts on the graph are where the function is decreasing, it's going down, and these are the intervals on which it's decreasing. So visually, we can see where these are, right? Okay, and we should notice a couple of things. We should notice that I included the endpoints in these intervals, right? I included 5, I included 2, I included 7. I know that because there's a less than or equal, and then -3 is included, 2 is included, 5 is included, 7 included. And so the question becomes, well, wait, why did you include 7 on increasing and then include 7 on decreasing? And so I'll let you take the time to read Brian's explanation here, and I think it's a very nice explanation about why we include the endpoints, right? When we talk about increasing and decreasing, we're never really talking about increasing or decreasing at a point. We're always talking about increasing, decreasing on a window of points, an interval. And so we include that point because in order to apply the definition of increasing or decreasing, we have to include the endpoints as well to be able to compare that to the next point. So remember, we're always comparing 2 points on any interval to see if it's increasing or decreasing, and that requires us to include the endpoints as well. So I'll let you read that. You can pause the video and read it, but I think we should accept that whenever we're talking about increasing and decreasing, include the endpoints, right? So if you'll notice, I always said less than or equal, greater than or equal in all of my interval notation. Okay, but here's the issue. We were looking at a graph, kind of easy to see where the graph is going up, where the graph is going down, which in turn tells us when the function is increasing, decreasing. But what if they don't give us a function? Or worse, what if they don't give us a graph of the function? Or worse, what if they give us a graph of the derivative of the function? Right? So we have to think of how can I use the properties of the function in order to help me determine whether it's increasing or decreasing. Excuse me. Well, there's one thing that can tell us when it's increasing or decreasing because it's attached to this idea, and that is the derivative. Because the derivative tells me the instantaneous rate of change. And a rate of change is how something is changing, which is what increasing and decreasing is telling us, right? The increasing and decreasing is about the rate of change. How is this graph changing? Is it going up? Is it going down? And so the derivative is going to be able to tell us that. And I'm going to skip ahead to point these two ideas out, and then we're going to go back into critical points. So here's the big idea that you need to walk away with whenever you're looking for intervals where a function is increasing or decreasing. If we have a continuous function, again, there's a condition. If we have the continuous function, then if the derivative of the function is greater than or equal to 0, then we're going to say that the function is increasing. If the slope is positive, then the function is increasing. Or if f prime of x is less than or equal to 0, then we're going to say that the function is decreasing. Again, if the slope is negative, then my function is decreasing. So it should be a little common sense that the derivative, which finds the slope, is going to help me determine where the function is increasing or decreasing, right? So in order to do that, we're going to need some critical values. Some people call them critical values. Some people call them critical points. I've even used a book that calls them critical numbers. But either way, the common thing is that they're critical. And in video 2, I'm going to tell you why.